Of course, I'm going to have this lecture for 30 minutes, and the remaining minutes we actually to talk about the midterm two, okay, which I've already published, and my TA is going to walk you through midterm two practice tomorrow in the lab. Okay, so I want to welcome you to this lecture, time series analysis. We started time series analysis this week. And of course, this is going to be the third time we're going to be meeting on time series analysis. And that was why I called it part three. So today, the focus is going to be on ARO modules and ACF plots. ARO modules, of course, we started ARO modules yesterday, right? We did a autoregressive module of order one, right? That's what we call ARO modules. So we have autoregressive module of order one, order two, and so on like that. Okay. But today we're going to look at the ARO modules, and we're also going to look at the ACF plots. The ACF plot is what we call autocorrelation function plot. Okay. So today I'm going to walk you through the significance of that. But before I move on, I first want to show you what I walked you through yesterday on autoregressive module of order one. As you can see the module specification, right? And the alternative way to specify ARO of order one, I walked you through that yesterday. And if you basically, when you want to talk about properties of stationarity in ARO1, of course, I showed you all that yesterday, the formula. If you're given a time series, or particularly ARO1 module, or ARO of order one, the expected value of YT is this, can be found using CO divided by 1 minus CO, C1. Okay, so I needed to pay attention to that. You see the formula here, right? Okay, so that is, and of course, you know where your CO is coming from the module specification, and you know your C1. All we just need to do is to plug that in, and you're actually going to get 8 as the expected value of YT. If you want to figure out the variance of YT, it's just going to be sigma squared W divided by 1 minus C1 squared. Of course, you know what sigma squared W is. That is the variance of the error. Take a look at this. In the specification of the white noise of the WT, that is trying to tell you the variance is 0.19. And of course, if you basically want to figure out the autocorrelation at a lag K, autocorrelation at a lag K, of course, is basically C1 raised to power K. Okay, don't forget, you know your C1, right? If your C1 is negative is 0.9, then autocorrelation at lag K is going to be negative 0.9 raised to power K. If they say what is at lag 1, just plug in K equal to 1. At lag 2, plug in K equal to 2. Okay, does that make sense? Okay, if that really makes sense now, we now want to demonstrate this in R with data set. We want to generate an artificial set of data. I need you to pay attention now. If we want to specify data, we want to simulate data. Okay, if we want to simulate time series data, for instance, I said I want to simulate time series data of 1000 in size. Okay, I'm actually going to write YT equal arima.sim. Okay, arima.sim. The parenthesis n equal to 1000. Okay, then I need to, if I want to simulate ARO of order 1, then I need to specify what is going to be my autocorrelation, my C1. I'm specifying my C1 to be negative 0.9. You see that? Then I'm also going to specify the standard deviation. The standard deviation, of course, that will be the square root of the variance of the error. you've been told like variance of the error is, of course, the variance of the residual is 0.19, then plus the mu. I'm specifying my mu to be 8. Okay, so which means what I'm trying to do is, based on this module specification, uh, based on based on this, you see what I circle, right? Based on that module specification, okay, this guy here is a code in R to simulate 1,000 data set, okay, that have that very feature. Does that make sense now? And that's exactly what I'm doing. Okay. Now, well, what is the meaning of setting seed? Set the seed equal to 2. If we don't set seed, okay, we're actually going to generate different data set. Don't forget, we are generating data set at random. There's so many billions of data set that your own 1,000 may be different from my own 1,000 may be different from. But when you set the same seed, when we put the same number on the seed, I'm putting 2. If we all put the same number on our seed, we will generate the same set of data. So setting seed is for reproducibility. Now, after doing that, I now plotted my data point over time. Take a look at that. Do you see the graph? That's a time plot, right? Okay, what is the code? Don't forget, YT is actually so if you take a look at this is the code to generate that particular time plot. So which is plot.tx YT. Look at that. That's generate that. That is the time series plot for 1,000 data set that we generate. You know what we want to do now? Please pay attention. Do you know that we know the theoretical mean and the theoretical variance of YT? Let me take you back. What is the theoretical mean? Expected value of YT is theoretical mean. The variance of YT is the theoretical variance. The Roy K, that's a theoretical autocorrelation. So what is the theoretical mean? 8. What is the theoretical variance? 1. And what is the theoretical autocorrelation? It's negative 0.9. So these are theoretical mean. But you know what I want to find out? From the data set that I've generated, I want to get a sample mean. Okay, how will I get a sample mean? Do you see the code? Mean it to YT. Oh my God. The sample mean is 8.01304. What was the theoretical mean? The theoretical mean was 8. You can see there's a difference between the sample mean and the theoretical mean. Theoretical mean is also called population mean. Does that make sense? Okay. Now, if you want to get the sample variance, it's just going to be var into YT. Okay. It's just going to be YT. Okay. I need you to take note of that. Now, what did I say? Since I simulated this data set, I already know the mean and the variance. But the mean and the variance that I know, that we're going to call them population mean and variances, or theoretical mean and variances. Now look at that. Are these estimated value close to the true values? You know, the theoretical mean and the population means they are the true values. Now, the sample mean that we got now is very close to 8. The variance that we got now, okay, we can actually look at that variance, compared to 1 that we got the other time. So take a look at that. Any question on that? You can see different exists between the sample mean and the population mean, okay, with regard to time series data. Okay, we already know the population mean and the population variance before we simulated the time series data. Now that we've simulated the time series data using the parameters, we now recompute the sample mean and the sample variance, and we basically want to see whether there's a gap between them. We're going to do the same to autocorrelation. Now, you know how to find a theoretical autocorrelation. The theoretical autocorrelation is using is this guy here. Give me 1 second. So the theoretical autocorrelation is that, right? That's a theoretical one. But if I want to get it from data set, then that would be that means I need a sample one. Does that make sense? Now, how do I get that? What will be the code? Please pay attention. This is the code ACF into YT. Don't forget, you use YT to denote the set of data you generated. The ACF into YT, you know what ACF is going to give you? Okay, ACF into YT will give you this. We give you this guy here. We give you an ACF plot. Okay, we give you all of that. Okay, but if you basically want to look at the way it is, you can look at it this way. Do you see ACF into YT plot equal to F means this time around I don't want plot. I only need the figures. Okay, and that F means false. If I go back here, when I say ACF into YT, it's going to give me, it's going to give us the estimated autocorrelation plot. Take a look at that. That will give you opportunity to see at lag 0, okay, it's going to be 1. Of course, there's an agreement between theoretical and the sample and the estimated one at lag 0. Lag 0 is always, look at that here too, 1. Okay, but there's going to be little difference when you go from row 1 autocorrelation at lag 1. Now let's look at the estimated. Estimated at lag 1 is negative 0. Okay, you're going to see now. This is going to give you an opportunity. Take a look at this. I want you to focus on this table here. There are two what? Autocorrelation at lag K. The first one is the population one. The second one is the estimated. The population one, do you know how we get the population one out? We use the formula. What was the formula? If you want to get the population one, you're actually going to use this one. C1 raised to power K, right? You're just going to be plugging in when K equal to 0, when K equal to 1, and so on like that. That's a population one, right? But for the sample one, is the one that you're going to write ACF into YT when you have your data. Now, this is going to give you an opportunity to compare them. They are not the same. But they're only going to be perfectly the same at lag what? 0. Does that make sense? Take a look at that. We see a cap on that means it's an estimated. The one you get from the sample. Does that make sense? Okay. You can know what is the takeaway from here now? The takeaway from here now is difference exists between theoretical mean and sample mean of a time series data. Theoretical variance and the sample variance, you see the difference, right? Now, the theoretical autocorrelation at lat K and the estimated. Take a look at that. Okay? Any question on this? So what we've done here, we compare the estimated autocorrelation against the true values. The true values, what we call the true values, is the population one, is the theoretical one. Does that make sense? Okay, now we now want to do something. How, you may be wondering, when you have a module specified, if AR1 module is specified as this, right? If AR of other one is specified like that, from the data set, how are we going to obtain 15.2 and the negative is 0.9? How can, like, you have a set of data, right? And you basically want to, it's just like the same way you did in regression type model, where you figure out regression coefficient. So what are we going to do? Okay, I want to walk you through that now. Okay, that's what we want to do here. MOD, you're going to write ARIMA. ARIMA. ARIMA means autoregressive integrated moving average. Okay, ARIMA, then YT is your data. Because I'm considering ARO of order 1, the ARO of order 1 is the same thing as ARIMA 100. Yeah, ARIMA 100 means the order of the AR is 1, integrated 0, moving average 0. We're still going to talk about all of that as time goes on. That is the code. Okay. As time goes on, I'm going to tell you the essence of, what is the one in the middle and the one at the other end. When I do that to the model, when I write the that code, what I'm trying to say now, when I write this code and I click on MOD, okay, this is basically the output. Do you see the output? That's it. That is the output. Okay. So that is the output that we have right now. Now, let me now tell you, do you know that from this output now, we actually want to know what is our C1, what's our C0, what is our mu? I want to confirm to you, when you have an output, from the ARO of order 1, your mu is always the intercept. Do you see what I circle now? 8.0134. That is the mu. That is not C0. That's a mu. Please take note. And that is what I'm trying to say here. Take a look at what I'm doing here. What I call that? That's actually mu cap. Not just mu, it's a mu cap. It's an estimate. What is the meaning of mu cap? Like sample mean, an estimate of population mean. Okay. Now you see SE, right? Like SE of 0.0133, 0.0072. SE means standard errors. Okay. Now, do you see something under the AR1? That is C1. What is the C1 now? Negative is 0.9066. What was the true values of the C1? When we first simulated that, it was a negative 0.9. But the estimated now is different. Negative is 0.9066. If I want to write my fitted model, I told you the other time there are two forms of a fitted model. We have one that is YT minus mu and equal to C1 into YT minus 1 minus mu plus WT, or defeated the other one. But let me tell you, I will advise you, if you basically want to write the the fitted model, I will advise that you always go with the one that have something minus mu cap. I'm talking about this guy here. Give me 1 second. I'm talking about this guy. If you want to write your results, if you want to write a fitted model, always for AR1, okay, that is what you're going to use. Now let's start substituting. What is your mu cap? The mu cap is 8.0134 from the output. What is your C1 cap? Your C1 cap is negative 0.9066 to 2 decimal. It's basically going to be negative 0.91. Do you see the next one? This guy here is after plugging in two things. After plugging in two things, the estimate of the mu and the estimate of the C1. If you now simplify that, you're basically going to end up here. Take a look at that. You're going to end up here. When you end up here, what is your C0 now? Your C0 is 15.30. What is your C1? The C1 is approximate. It's now negative 0.9. Take a look at that. Any question? That's our fitted AR1 model. Now I just walk you through how to fit an autoregressive model of order 1 to time series data. And that is where to write the fitted model. Okay. Now that we've done that, okay, now that I've walked you through how to do that now, we now, when you fit a model, when we fit a model like this, how do we know the model is going to do a great job? Oh, we've already fitted an ARO of order 1. But let me tell you this. I know this model will do a great job. You know why? Because I simulated it from the data set that I used is from AR1. When I was simulating the data, okay, don't forget, what are the parameters I used? Mu was equal to 8. I set mu to be 8, and I set C1 to be negative 0.9. Does that make sense? Do you see how we know in statistics whether this model will do a great job? What we normally do is, if we already know what happened, we now want the model to dictate that. Like right now, I fitted an AR of order 1 to the data set that I know is AR of order 1. But let me tell you this. In real life practical situation, you are not going to simulate. You are using real life data set. You don't know where they come from. So in that situation, you're going to have series of analysis you're going to conduct before you can actually fit the right model. But right now, you know what we're doing? With the data set we generated, okay, was from AR of order 1. Now, we fitted AR of order 1. And you know what we want to do now? We now want to investigate whether the ARO of order 1 we have fitted to the data is appropriate. Of course, it's we, because the data set used, we use ARO1 parameters in simulating them. But let's see. Now, in the model diagnostics, this is where the white noise. We need a white noise here now. You know the other time I told you, when your model is entirely white noise, that's a bad model, right? But in model diagnosis, when you want to actually subject time series model into diagnostic testing, the way to investigate a good model is to investigate whether the residual behave like a white noise. If residual behave like a white noise, then we are fine. Now, if I want to investigate that, you know what I'm going to do? Take a look at this. I'm actually need to obtain residuals, just like the same thing we do in linear regression, right? In linear regression, we obtain residual, and we actually conduct analysis on residual, right? Okay, now take a look at this. Plot.tsmod residuals. That's what I have. If you see the residual plot, like in the case of linear regression, if we want to verify whether linearity assumption hold, we don't expect residual plot to have a pattern. You get what I mean? But right now, if you take a look at this, okay, you can see that the plot revolve. Okay, on average, it revolve around 0. You see that? You see all of that. This is what I'm trying to say. On average is, you see that? That is within what? Within zero. Okay? So the averages of residuals are approximately zero. Oh, this is also looking like assumptions in linear regression where the expected value of error equal to zero. Expected value of error means average of the errors. Here we're talking about average of residual. So one of the way to investigate is to use a time series plot, a time series plot of residual. Okay. Then we're also going to look at the constant variance. Don't forget, we said something the other time, right? In the time series, assumptions in time series is a scenario assumption. Assumptions of linear regression, you have linearity, normality, constant variance, independence. But in time series, there are three, everything, there are three things, there are three basic measures that we need to put into consideration. And the three measures are focusing on stationarity. Number one, mean have to be the same over time. Variance have to be the same over time. Not only that, the autocorrelation function at any lag should be what? Should be zero, right? For white noise, right? That's what we want to investigate now. Now, when we take a look at this now, the mean and variance are constant over time. That's all we mean. Because if you take a look at that, okay, which means both of them are consistent with the properties of the white noise. Now, let us now look at the ACF, autocorrelation function plot. Now, the autocorrelation function plot that we want to talk about, now, there are two autocorrelation function plots. The one we are interested in is the one for residual. It's different from the one for the data. The one for the data is this one. Oh, sorry. The one from the data is this one. Do you see this guy? This is the one from the data. But the one for the residual is what we want to talk about. Okay, now if I want to get the one from residual, MOD $ residual, ACF of that, oh my God, look at the blue dotted line. What happened? Apart from autocorrelation at lag zero, I'm referring to this. I'm referring to this guy here. Apart from the autocorrelation at lag zero, of course, autocorrelation at lag zero is always going to be 1. Does that make sense? Now, every other autocorrelation at the other lag, they fall within 0. Can you see that? And that is one of the properties of a white noise. You remember when I was walking you through, okay, autocorrelation at lag 1, lag 2, lag 3, they're all going to be 0 for white noise. What is it telling us? The model is appropriate. Okay, the model is appropriate because residual behave like a white noise. How do I know residual behave like a white noise? Because the autocorrelation function plot of the residual here, they are all within 0. Okay, as lag increases. Now, this is how to investigate that. Any question? So that's how to investigate the validity of a model. I told you the other time, we already know that the model will be appropriate. Now, if you now have real life data, Google stock price now, okay, and we now want to fit, give me 1 second. Give me 1 second. Click on why I'm trying to correct something. Is there anyone who need clarification on what we're doing now, of what I've explained? Is there anyone who need clarification, whether or online? Is there anyone? Okay, I need someone online to confirm again if you are hearing me clearly. Is everyone hearing me clearly online?
And
Yep.
confirm.
Okay, thank you so much for confirming that. Okay, so I'm going to go back into the material again, and I need those online to confirm if you're seeing the. I think what I want to correct it, that since it came, give me 1 second. I'm going to see why is not. So you can use this opportunity to ask question, if you have a question to ask. Okay, so I'm going to reshare that again and see what happened because that character didn't come out well, so that's why. But I'm going to share that again and see. But the one you have is PDF, so I converted that to the PowerPoint, so I don't like the character. So let me see change what we want. Okay. Okay. You got that example still come down. But I'm gonna tell you what you have there anyway. Okay, now we want to use real life data set. So we have saved daily adjusted closing price of Google stock. So the daily price from April 2022, I mean April 22, 2018 to April 22, 2019. Okay. What is the first thing you're going to do when you have data set? You generate a scatter plot, right? For when you are doing linear regression, right? But for time series, you're going to generate a time series plots, okay? Which is like plotting the data, like we're plotting the Google price against time. Does that make sense? That's what you have here. And this is the code plot.cs GOOG. Those of you online, can you confirm if you are seeing my lecture slide?
See,
Okay, you're seeing it, right? Okay. Now, the next thing you're going to do is to generate the ACF plot. You remember when we started the other time? We generated the ACF plot for the data we simulated. But right now, this is a real life data. Why are you doing that? Is to see whether it should fit AR1 or not. Because the AR1 is going to, okay, when the ACF decay exponentially to 0, okay, yeah, I said the ACF plot show decaying estimated values, and that could be an AR1. I'm going to suspect AR1 if the autocorrelation at lag as lag is increasing, okay, if the autocorrelation is going down, is decreasing, now I'm going to think about it fitting AR1. Now I want to fit AR1 to the data, okay. My data is GOOG, MOD equal to ARIMA, okay. Then ARIMA order 100. Do you see that? You see the output, right? Now you want to write the feeder module, okay, based on what we did before. Okay, this guy here, give me 1 second. This guy here now is the feeder module. You know the estimate of the intercept, that's 1135.1945. You know how we plug that in the other time, and the ARO is 0.9691. That is our feeder module. Now we building module for Google price. Why are we building module for Google price? Because we'll use this module to make a prediction. Don't forget the price changes, right? There's a lot of volatility in the market. Okay, now, but before I'm going to use this to make a prediction, I need to first investigate whether this is a valid model. Now, if I want to investigate, what am I going to do first? I'm going to generate the time plot for the residual, right? Why do you think I'm interested in doing that? I want to investigate whether assumptions of stationarity hold. Which assumption? Mean is on average, it's mean the same over time, variance the same over time. You get what I mean? That is why I generated that first one. Then the second one is autocorrelation function plot for residual. And for residual to behave like a white noise, we expect, you know, uh, the autocorrelation from lag 1 all the way to be 0. But I want you to take a look at this. You will see that I think about 2 marginally came out of the 0, right? Do you see that? Do you see what marginally came out of? Don't forget, we're using real life data, okay? And our module cannot capture exact reality, okay? Now I said, based on the ACF plot, most of the estimated autocorrelation are close to 0, okay? The estimated autocorrelation at lag 10, if you look at lag 10 at lag 23, exceeded the boundary, right? So which means autocorrelation at lag 10 and autocorrelation at lag 23 are significantly different from 0. Does that make sense? And I said, since the significance level is 5%, let me tell you this. We set significance level at 5% because we know you know what 5% means? That means we're actually going to mislead people 5 times out of 100. We still fine because 2 points out of so many points, that's not enough to say the model is not good. Does that make sense? And that's exactly. So yeah, I say we can conclude that the residual behave like a white noise, even though it is not all, but majority fall within 0. Okay, and 5%. Okay, because for something to be significant, we set an error of 5%, provided it does not go beyond 5%. We are fine, right? Okay. Now, this is giving us the idea that the model is fantastic. Then you can now go ahead and use the model to make a prediction. Don't ever try making a prediction without you first subjecting your model to diagnostic testing. Now, what do you want to do now? The model stop at 250, right? If you know what we simulated, okay? See, our data include the daily adjusted closing price of Google stock from April 22. It's a daily data from 2018 to April 22, 2019, which is going to be 251 observations. What do we want to do? You want to make a prediction for the next day. What will be the next day? That will be observation 252, right? Your data point stop at 251. If where you have a YT in the model, if you put 252, okay, now you recall your observation 251 is 1248.84. That one will come from your data set. If you plug that in, okay, when you make a prediction for the next day, it's going to be 1245.44. The code now to do that is this guy here. Do you see that code? 1 ahead prediction, just for 1 ahead. Like my data stuff today, I want to predict for tomorrow if I'm working with the daily data. Does that make sense? Now, when you take a look at what we have, okay, that is what you now. Do you know you may want to do something? Maybe we already know. I know that day is going to be April 23, 2019. That's what we want to predict for, right? You know that your data stop at April 22, 2019. You now want to make a prediction for April 23, 2019. Okay, we had our prediction now, but can we compare our prediction with what really happened that day? Oh my God, to know if our model is telling the truth. What happened that day when you look at the when you look at the website was 1264.55. Now, can we measure a distance between what our model predicts and what happened that day? That's exactly what I'm doing here. that I said the original minus predicted, the actual observation minus, and that gives us 19.22. If you want to look at 19.22 in terms of percentage, that's just about 1% of the price. So our prediction is not bad because I don't really expect my model to give me perfect prediction in the first place. Does that make sense? This is how to fit an autoregressive model of order one. Okay, I want to use, okay, go ahead. You are really telling the truth. That is it. Because it's just within 1%. I can use 5% boundary here because that's a standard. You are right. Very correct. Very, very correct. Okay. So, I've already sent um, the midterm to material to my TA to walk you through. And let me tell you this. I'm basically going to follow that pattern in the exam. Does that make sense? So my TA is going to walk you through midterm 2 practice question tomorrow. That will be the trend of midterm 2. That is the way I'm going to ask my question. I'm not saying exact question. You get what I mean? I'm talking about the question will focus on the area, the same area those questions focus on. So please, I needed to pay attention. Now, the new information is, or let me first start with the old information. The midterm 2 will be open by 6 p.m. tomorrow. And it's going to be left open for 29 hours. It will be, I think the latest is going to be 11:59 p.m. on Saturday. If you want to start, you can start at any time, but you need to join, you need to log on to the Zoom. The Zoom is being recorded. You turn on your video, even though I'm not going to be there, but I want to see somebody behind the scene writing the exam. Okay. And of course, like I said, you're going to have access to the exam 6 p.m. tomorrow. It's going to be left open for 29 hours. You can start at any time. Okay. So like I said, the exam will focus on the midterm 2 practice question area, the one that my TA is going to walk you through in the lab tomorrow. If I were you, make sure you attend the lab tomorrow. Of course, it's already uploaded. I uploaded the midterm 2 practice solutions, the one that I want my TA to walk you through. Is there any question before I go today? Is there any question? So because I still have 5 more minutes, I'm going to have a recap on the autoregressive model of order 1 and the use of ACF plots. In summary, what is what we've done today? Today, we've been able to see there's a difference between theoretical mean, theoretical variance, theoretical autocorrelation, and the estimated one that we call the sample. We simulated that set today, okay, using the AR1 parameters. When I talk about AR1 parameters, I'm talking about, the autocorrelation value and the standard deviation. And of course, we simulated, and then we find the sample mean. We compare the sample mean with the population mean. We discover that they are not the same, but they're very close. We compare the sample variance with the population variance that are also called theoretical variance. We realize that they are not the same. We also compare sample autocorrelation with the population autocorrelation. We realize they are not the same. Let me tell you, in the study of time series data, what we always do, mean variance and autocorrelation, they are very crucial to absorption in time series because the time series model requires stationarity assumption. It requires that the mean and variance should be constant over time, And not only that, the idea of autocorrelation will be used when we basically want to know, what kind of model we're going to fit for the time series data. Not only that, the idea of autocorrelation is also going to be used by the time we are trying to subject the model to diagnostic testing, where we're basically going to generate what I call the ACF for the residual. There are two plots, ACF plots, okay, ACF plot for residual and the time series plot for residual. Let me tell you this. There are 4 plots in general. The very first plot is the time series plot of the original data. The second plot is the autocorrelation function plot for that data. The third plot is the time series plot for the residual. And the fourth one is the autocorrelation function plot for the residual. So the autocorrelation, the time series plot for the residual will enable you to see the behavior of the mean and the variance over time. The autocorrelation function plot for the residual will enable you to see the behavior of the autocorrelation function value when lag increases. Okay, when lag increases, we expect, all of that to be within 0. It may not necessarily be all of them, but the majority of them, if you use a 5% threshold, majority of them should be within 0. Okay, and after that, if everything is good, then the next thing is to make a prediction. But don't rush making prediction without ensuring that your model is adequate. Otherwise, whatever decision you take, okay, if we normally make a recommendation that will form part of policy formulation. The moment the model that we are actually making a recommendation from, the moment there's a violation of assumption with that very model, whatever decision we take, we're actually going to be declared null and void. And that is why at times it looks as if our models are failing us. Our models are not failing us. Are we doing the right thing? Doing the right thing is to investigate whether assumption hold. And that is the story for today. Any question? Any question? In that midterm too, I will be the happiest professor ever if the minimum is 99. Is that not possible? That's possible, right? So make sure you attend the
It may be
uh
possible, but
okay.
it's statistically improbable.
Somebody said maybe it's possible, but statistically improbable, right? Okay, but let me tell you this. I don't believe that probability can be 0 or 1. I don't believe that. Even though in theory, probability can be 0 or 1. In this world, there's nothing that is certain, right? And I'm also going to say there is nothing that is uncertain too. So I expect things to lie between uncertainty and certainty. Does that make sense? So I'm not going to totally rule it out. It's possible. Does that make sense? All what you just need to do is just try your best, take your time, review what you're supposed to review, and believe you can do it. Because if you really want to do something, you have to start by believing in yourself. If you don't believe in yourself, that may be difficult to do. Does that make sense? So yourself believing, even though it is difficult, it's just a matter of time. You're going to figure it out. Just take your time, and you'll be celebrated. Does that make sense? Okay, make sure you all stay safe and have a very lovely weekend. Bye for now.